So, do a review of, talk about just the basics of waves and do some problems. So, yeah, waves are difficult to define precisely what they are because there's so many types of waves. But the basic idea is it is a disturbance that travels through some medium, and waves carry energy and momentum. And examples of waves, waves in water. You can have waves in solids. Sound waves are waves in air. Light is a wave. It's called electromagnetic radiation. So more than just light that, if you think of light as, you tend to think of the light you can see. But there's a whole electromagnetic spectrum that has radio waves, visible light, microwaves, X-rays. Those are all called light. And there's also some other kind of waves that are kind of interesting. There's like gravity waves, which are waves in space itself. And that's because there's so many different types of waves, it's kind of difficult to define precisely what they are. But the things they share in common is it's a disturbance that travels through a medium, and they carry energy and momentum. Now, there's two main types of waves. We have, let's look at a wave on a string. So if you grab a string, and say like grab one end and just shake it up and down, you'll create this wave that travels down the string. So the wave is propagating to the right. Now let's say we put like a mark on the string. So we put a red dot on the string, then we shake this up and down, and the string, like if we look at this one point, that's just going to go up and down. So this is called a transverse wave. So the wave is propagating to the right, but the medium, the oscillations are perpendicular to the direction that the wave is moving. Now, on the other hand, we can have another type of wave. Say we have a slinky, and say you grab this end and just shake it back and forth this way. So if you look at one coil, we just focus on that one coil. The wave, if you just say push this, you can see the wave traveling down the slinky. And if you look at just this one coil, as the wave goes by, the slinky is going to oscillate back and forth in the direction that the wave is moving. So these are transverse, I'll just call it T, and waves like this, where the motion of the, whatever makes up the medium is parallel to the direction that the wave is moving. Those are called longitudinal. And again, these are kind of idealized cases because in general, waves can be more complicated than this. An example would be like the surface of water. Like if you drop a rock in the water, these waves spread outwards. If you look at the actual water, it goes through more of a circular motion. But you can break that up into pieces, like a transverse and a longitudinal wave. So like as it's moving up, it's moving across and it'll trace out a circle. So these ideas are very important, transverse and longitudinal waves. Okay, speed of a wave. So waves travel through a medium. They travel with a particular speed. What's kind of interesting is that the speed of a wave doesn't really depend on what caused the wave. Like say you have a metal pipe or something. You can get a sound wave traveling through the pipe until you hit it with a hammer. then you'll cause a wave to travel down the pipe. And you might think if you hit the hammer harder, the wave's going to travel faster, but that's not the case. The speed of a wave depends on the medium. And there's actually kind of a general result. Like you can write down the speed of a wave in general, but we're not going to do that. That's something that involves quite a bit of calculus to understand. So to actually figure out the speed of a wave, it's kind of a difficult thing. And so what, basically in the notes, we looked first at, say, a wave on a string. That's an important example. And we didn't derive this result. It's kind of difficult to derive. And so what I did is kind of took a few experimental facts. So if you have a wave on a string, the speed of the wave depends on the amount of tension in the string. And this mu, I should have written it up here. Here we go. Mu is the linear mass density. So that's like the mass over the length. So that would typically be measured in, maybe like milligrams per centimeter for a string. Strings are very light, but yeah, I mean, the basic SI units would be kilograms per meter, but obviously that's 1 meter of string is going to be significantly less than a kilogram. So maybe grams or even milligrams per centimeter would probably be the appropriate units there. And so it depends on the density of the string as well. Like you can have a dense string or a lighter string, waves will travel at different speeds. And so we're just going to take those as experimental facts. And then we did something interesting called dimensional analysis, where if we take these things like tension, mass, and length, how can we put these things together in a way that will give us the right dimensions? So like meters per second, if we stick to particular units. And the only way you can really combine these is it has to look something like this. Let's just check the units really quick. Tension, we have a Newton over, say, a kilogram per meter. And then we take the square root of that. But a Newton is a kilogram meter per second squared. We can cancel out newtons, cancel out kilograms. We have meters squared per second squared. And then we take the square root. And this right here, this result is dimensionally correct. So that gives us an idea of what this kind of should look like. But that doesn't mean that just because the dimensions work out that that's the correct answer. It could be 2 times the square root of t over mu, or it could be like 100 or 1,000,000 times that. But it turns out you can use Newton's laws and actually find the speed of a wave on a string. And it turns out that what we did with dimensional analysis is the correct answer. Just happened to work out perfectly. Yeah, that idea of dimensional analysis, where you figure out how to put an equation together that just has the right dimensions, that turns out to be way more useful than it sounds. In this case, it actually gave us the correct answer. So, yeah, you can't expect that to work, but in this case, it did. And then for other materials, say we have a gas that is like a single molecule or atom. So you could have like hydrogen, which would be a molecule, H2. The hydrogen atoms, they each have 1 electron. If they combine, they have 2 electrons. That completes the shell, and they're happy. But helium is happy on its own. So helium, that would be just atoms of helium. But yeah, so this is the speed of a wave in a gas. So I should probably tell you what these things are. Gamma is a number. And this depends on what type of gas it is. It's usually a number like 5/3, for example. It depends on the details of the gas, like whether or not it's a monatomic gas or a diatomic gas, or even something more complicated, like say carbon dioxide. You have a carbon and 2 oxygen atoms. So yeah, like gamma, it would depend on the number of atoms or molecules that make up the gas. And it also depends on temperature. It depends in a very interesting way on temperature, where you can get values that kind of almost like they remain steady at very low temperatures, but then once the temperature reaches a certain point, gamma will change kind of suddenly. And so don't worry too much about gamma. Just say like every gas at a given temperature has a value for gamma. And K is very important. That is called Boltzmann's constant. I'll write it out. 1.38 times 10 to the minus 23rd power. The units are joules per Kelvin. Now, Kelvin, that is a unit of temperature. It's basically like Celsius, except it's based on absolute zero. So that's a fundamental constant, like one of the most important constants that just makes up our universe. And it's named after a guy named Boltzmann, who was this really brilliant physicist that kind of wasn't really recognized as well as he should have been in his time. This was the late 1800s, and his work was on gases where he treated them like atoms. And they didn't really, the scientific community didn't really fully accept the idea of atoms until the early 1900s. Kind of amazing that the very idea of atoms as being like established in science is, you only have to go back a little more than 100 years before that was controversial. So we've come a long way. Now, T is the absolute temperature. So what that means, absolute temperature, you have to use a temperature scale based on absolute zero. So again, if you take the next class in the sequence, you'll learn about absolute zero. Very basically, you can look at that as kind of a limiting temperature. If you cool things down, it takes energy to cool something down. And if you want to take something at room temperature and say cool it down by 1 degree, probably doesn't take that much energy. But then if you want to lower it another degree, you'll find that it takes a little bit more energy. And then like every degree that you cool something down, the amount of energy required keeps increasing. And it turns out that even with an infinite amount of energy, there's like a limit to how cold you can make something. And that's called absolute zero. And it kind of makes sense that this temperature would have to be based on absolute zero. Because if it's cold out, you can have a negative temperature if you use something like Fahrenheit or Celsius, and then we'd be taking the square root of negative numbers, and we don't want to do that. Okay, now M is, we can look at that simply as the mass of a single atom or molecule in the gas. However, it's not always that simple, because most gases are not just a single thing, like hydrogen or helium. Like air that you're breathing right now, that's mostly nitrogen, but there's also oxygen and carbon dioxide in it, maybe a few other things. And it's mostly nitrogen, oxygen, and carbon dioxide. Those are the big three, I'm pretty sure. Oh yeah, water vapor. And so what if you have a combination of different molecules that make up the gas? Then M is kind of like an average. So you need to know like what percentage, like air is like 78% nitrogen or something like that. And so you'd have to kind of weigh each molecule. So based on like the fraction of the entire gas. So for if like, I'm not sure of the exact number, but let's say the air you're breathing is 78% nitrogen, then you do like, 0.78 times the mass of a nitrogen molecule. And then if it's whatever percent oxygen, you take that percentage times the mass of an oxygen molecule. And again, I'm saying like nitrogen molecule and oxygen molecule because that's what they are. They would be like N2 and O2 primarily, like two nitrogen atoms combined or two oxygen atoms combined. Okay, so again, that's the speed of sound in gas, or the speed of a wave in gas, otherwise known as the speed of sound. You've doubtless heard of helium balloons, where if you inhale a helium balloon and then you talk and you sound real funny, that's because helium has a different mass than the air that you're breathing, and so the speed of sound will be very different. So that's why helium balloons work the way they do, or the sound effect you can get from that. It's kind of funny that it seems like an incredibly stupid way of using helium, because helium is actually something that we have a finite supply of. And it has some very important applications. And it used to be regulated by the government because it's a product of nuclear waste, like radioactive decay. But once you use it and release it in the environment, it's gone. You can never get it back. And that's one of the things that we'll be running out of or having shortages of in the coming decades. Probably not the best use is inhaling it and or just inflating balloons with it. But anyways, let's go on to these other two speeds of sound. This is the speed of sound in a solid, where that Y is called Young's modulus. Young was a kind of an interesting scientist. He was just known as kind of an all-around genius in his day. I think it was in the 1800s, like early to mid 1800s. He was a great scientist and mathematician and all sorts of other things. If you heard of the Rosetta Stone, the actual stone, not the company, that it was like an Egyptian tablet that had hieroglyphics, which, a lot of things in Egypt have hieroglyphics, but it also had like some other language on there. And it was translating this that allowed us to understand hieroglyphics. And Thomas Young was one of the people that did that. So it's kind of a rare exception to this, but usually if you're good at science, you're typically not very good at anything else, but he was an exception. And this Greek letter rho, that's the mass density. That's the volume mass density. So mu is called the linear mass density. That's a mass over the volume. Mass over length. Rho is mass over volume. So that would be like kilograms per cubic meter would be basic SI, but typically a much more common unit for density is grams per cubic centimeter. It's very convenient that I think the gram was defined so that water has a density of 1 gram per cubic centimeter. So it's a nice way of measuring density. Now on top, it seems like we have the word bad. It's actually B subscript AD. And so B is bulk modulus. So this Young's modulus and bulk modulus, these two things are very similar. Young's modulus applies to solids. Like say we have a concrete beam, like say in a building, this could be like a support beam, like a column to support a roof or something. And so if you have this column by itself, say you place a large mass on it, the column is going to be compressed a little bit. Now things like concrete and steel are not very compressible. But if you apply a large enough mass, yeah, they can compress a bit. And Young's modulus is a property of a material that tells you like how much this material is compressed given like the load applied to it. Now, typically, if you want to know Young's modulus for a particular material, you look it up. So just an idea of what it is. And similarly, for liquids, we have this bottom expression where B is the bulk modulus, and it's kind of the same thing as Young's modulus, but for fluids. So if you have a volume of water or a fluid like water, oil, whatever, if you apply pressure to it, you will compress it. Now, fluids are very difficult to compress. Think if you take water at, say, sea level and bring it down to the bottom of the ocean, its volume will compress by just a couple %. So, but does exist, but fluids are also very difficult to compress. And bulk's modulus, that relates like the change in volume that you would get, how that relates to the pressure. Now, what about that AD? That stands for that word adiabatic, which you may have never heard before. If you take the next class, 122, you will learn about that word adiabatic. But basically what that means is that there's no heat exchange with the environment. So like say you have a fluid, and the reason why it's important to know if heat is exchanged or not is, let's say that you compress a gas, you're gonna lower its volume. But what if, say, heat flows into the gas when you're compressing it? When you heat things up, they tend to expand. And so that can be a factor whether or not heat is entering or leaving the system you're looking at. And when it comes to sound waves, like waves traveling through a material like a liquid, they tend to move very quickly. They're, if you have like compression waves, they move extremely rapidly. So we have these rapid pressure changes, and they occur too quickly for heat to have any significant effect. So if you compress something, say very slowly, maybe there'll be time for heat to enter or leave, and that could affect how the volume responds to that change in pressure. But for sound waves, like a wave propagating in a medium, that's not a factor. And so this is called the adiabatic bulk modulus. So that's the one that we would want to use. And again, that's something that you would just look up if you wanted to calculate the speed of sound in a fluid. You would typically look it up, or in a problem it would be given to you. Now you might want to calculate the adiabatic bulk modulus, but if you were doing it, like there's kind of two ways you could calculate the bulk modulus for a material. One way, in theory, you could look at the actual material itself. Like say you have water, you have a bunch of water molecules, and they're interacting with each other through electric fields. And what's going to happen if you apply a force and try to compress it? That would be an extremely complicated thing to do, to try to derive this by looking at what's going on a molecular level. We're not even going to touch that. But you could have a problem where you're given, like, say, the speed of a wave in a fluid, and you're given the density, and then calculate the bulk modulus. Well, then you would just use that equation. So in any other case, you'll just be given the bulk modulus if it comes up in a problem. Okay. So that's the speed of a wave. Now, we also want to talk about the mathematical description of a wave, which I wrote here. So let me draw a transverse wave here. Although the same type of thing would apply to a longitudinal wave. Well, let's say we have a wave on the string. And let's say we take a picture of it. Say the wave is propagating to the right. And so let's say at t equals 0, the wave looks like this. Now we're not going to like derive the whole thing again, but we could describe this as, actually, let me move this over. Like sine and cosine are literally the exact same thing, just offset. So if you take like a sine wave, just move it over, you can get a cosine wave. But they have the exact same shape. Okay, so the amplitude of the wave, like at any point, is given by y. And that depends on x. So in this case, we could describe this wave at a given moment in time. Say A is the amplitude, and then we have the cosine of something times x. We get to say cosine x for two reasons. One, x has units, and you don't want to take the cosine of something like a meter. So that's one reason. And another reason is that you could have a different wave with a different wavelength. So this is a wavelength. So you go from like maximum amplitude to maximum amplitude. That's a wavelength, which is given by lambda. And so to get this to work, to take the wavelength into account, say 2 pi x over lambda. So if x equals lambda, then we have the cosine of 2 pi, which is 1, and we're back to our maximum amplitude. So this describes a wave with a particular wavelength lambda. However, the wave is moving, and so to take time into account, you know, to like shift the function. Like if you want to take the entire function and move it a certain distance, you replace x with, say, x minus a. That'll shift the wave a units to the right. And so basically what we do is we shift this to x minus vt. So that in a given time, the amount that it moved is equal to the velocity times the time. And so we can also plot the amplitude of a given point on the wave as a function of time and kind of go through the same analysis. And if we put it all together, we get this as our mathematical description of a wave. Now, this is a function of two variables, so we can't plot it. Like a function of a single variable, like here, y is a function of x. So we have one variable, that's a two-dimensional plot. If we want to plot a function of two variables, we have to make a 3D plot. You can try to fake it on a two-dimensional surface, but kind of difficult. There are some computer programs that do that. But generally, it's good to focus on one or the other. So like here, we can say at t equals 0, the wave looks like this. Or if we pick a single point on the wave, let's actually pick this point right here. If we just, so as a wave passes by, actually, let's do this one. So if you just look at that point and plot the amplitude at a fixed x value, but plot it as a function of time, then you can see what happens. We start out at 0 amplitude, and then it's going to start rising because the wave moves to the right. This point is going to go up, and so you get a function that looks like that. And so again, you don't really need anything new here. You just set x equals 0, and you have, or x equal whatever value that is, and then you get the amplitude as a function of time. And so it's good to kind of just focus on one or the other. Now, if you look like right here, we've completed a full cycle. Back where we started, we're going to, like here, we're kind of back where we started, but here we were going up, here we're going down, so we haven't really completed a cycle. So here's when we complete the cycle, and the time it takes to complete the cycle is the period. And so I wrote here this lowercase f, that's the frequency, which is 1 over the period. Okay, so that's kind of everything in this topic that I wanted to review. So we'll do a couple problems, but before we do any problems, are there any questions on anything? Okay, so let me pick out a couple problems and just grab something from the book. So I'm going to kind of make something up. Say we have a string with a density of 65 grams per meter. And so that's just the string that we have. Tie one end of the wall, the other end goes over a pulley. And we have a mass of, say, 1.2 kilograms. The question is, what is the speed of the wave? So say you just flick the string. By the way, if you look at stringed instruments like guitars, there's different strings, there's different densities, so we can get different wave speeds. But you can also tighten and loosen the string, and by doing that, you're adjusting the tension. So by tightening it or loosening it, you can change the speed of the wave, and they're kind of fixed to be a certain value, like certain tension in the strings. But if it's out of tune, you can fix it by adjusting the speed of the wave. So you do that by changing the tension. And so say we create a wave on this string, how fast is it going to go? So first off, we need to know the tension in the string. And that's just going to be mg. Because this mass is hanging here. So remember, if you have a moving mass, then it does not necessarily, the tension is not necessarily mg. If your mass is falling at a constant speed, tension would be mg. But if it's accelerating, then tension is not equal to it. So let's put this together. Actually, we want to be a little careful. Yeah, I think it'll work out. We have two masses in a way. We have a mass of weight, and there's also a mass density. So just make sure we don't get confused on that. I'm going to square it just so we don't have to worry about the square root at the moment. So V squared then would be tension, which is mg over the mass density mu. Let's see, we have 1.2 kilograms, 9.8 meters per second squared. Mu is 65 grams per meter, and then there's 1,000 grams per kilogram. So let's look at the units. Here we have kilogram. I'm going to write meters squared because we know that's not going to cancel out. was this even necessary? Yeah, we did need that conversion factor. Okay, so on the bottom we have seconds squared, and then grams, and then kilograms. So what we get are meters squared per second squared. So let me just see, 1.2 times 9.8 times 1,000, and then divided by 65. So I'm getting about 181. So what I'm getting here, by taking the square root of that, is about 13 meters per second. So that would be the speed of the wave in this case. And if you hang a heavier mass, what's going to happen is the tension is going to increase. And so the speed of the wave will increase as well. Okay. So any questions? I mean, that's a pretty straightforward. Find the speed of a wave on a string. Any questions on that? All right. Let's see what else. Let's do something with the mathematical description of a wave. I'm going to get rid of this problem. So here's one. Okay, so a wave has the following properties. Amplitude 37 centimeters. Period is 0.77 seconds, and the wave speed is 12 meters per second. And it's traveling in the minus x direction. So we have a wave, we can describe it it's moving this way. Oh yeah, so talked about shifting a wave. So the actual formula, we should actually have a plus or minus here. And because a wave can be moving in either direction, and so you use the use a plus or minus that tells you which way the wave is moving. And if wave is moving to the right, we use a minus sign. Moving to the left, we use a plus sign. So let's look at what they're asking us. What is the mathematical expression? It's similar to equation 16.3. So might as well look that up. Yeah, so they're using a sine function there. So we want the mathematical, we want to write the amplitude of the wave as either, you can use a sine or a cosine function, doesn't really matter. They used a sine here. Okay, but let's use cosine. Doesn't work, doesn't matter either way. So we have our amplitude. Now, one other very important property of waves that I did not write down is that the speed of a wave is the frequency times the wavelength. So we might need that as well, because they gave us, we don't have the wavelength of this wave, which we'll need, but we can find it because the wavelength would be, if we know the speed and frequency, we can find the wavelength. We're not really given the frequency, but we're given the period, so we can find that. So yeah, let's actually do that first. I'll do it and then erase it. Let's find lambda. We'll write down the result and then maybe erase it if we need the room. But the wavelength is the speed over the frequency, or the speed times the period, because frequency is 1 over the period, so we put the period back on top. So here we have 12 meters per second times 0.77 seconds. So we'll get meters here. 12 times 0.77, this is 9.24 meters. Okay, so yeah, let's say we have a cosine, and then we have 2 pi x over lambda. So that'd be 2 pi x over 9.24 meters. And then let's try plus 2 pi times the frequency. The frequency is 1 over the period. So 1 over 0.77, that's about 1.30. Inverse seconds. Now there's a name for an inverse second. We measure frequency in units called hertz, which are inverse seconds. But because we're going to plug it into this formula, let's just leave it how it is. So we have 2 pi times the frequency. Hey, let's do this. 2 pi divided by 9.24 is 0.68. All right, so I just replaced 2 pi over the wavelength of 9.24 meters. Numerically, that's 0.68 per meter. So if we plug in x is like 1 meter, we just get 1 times 0.68. And now, because the wave's moving to the left, let's use a plus sign here. So 2 pi times the frequency, let's do that now. This is 8.2. And that would be times time in seconds. So 2 pi times 1.3 over a second, that's 8.2 over a second. But if we just write them like this, where if you plug in x in meters and times in seconds, units will just cancel out. So that's a mathematical description of this wave. So that's one thing you should be able to do. If you're given this information, you were given this information up here, you should be able to write down the mathematical description of a wave, but you should also be able to do the opposite. Like say, let's actually do this. So I'm going to erase the values. Let's say I give you this, that a wave is described by this function. Let's say I asked, what is the frequency of this wave? So you should be able to find the frequency. The amplitude doesn't really matter. So if I give you this equation and ask you to find the frequency, but you look, it's in this form, we can see that here in front of x, we have 2 pi over lambda, and we already know these values. But let's say we didn't, so let's calculate them anyways. So we could just look at, just by matching this up, here, let's say I also ask you for the amplitude. That one is easy. It's right here. So you just write down the answer. But then if I ask you for, say, the wavelength and the frequency, Lambda, you would look at it and say, well, 2 pi x over lambda. Here we have, we can say that 2 pi over lambda is 0.68 over a meter. So basically 0.68 over a meter is 2 pi over lambda. That would match up to our equation over there. So if we solve for lambda, we'd have 2 pi times a meter over 0.68. So let's do that. 2 pi divided by 0.68 is 9.24 meters. And to find the frequency, we can say 2 pi f times t. A formula, we have a what's in front of that t is a 2 pi times f. So we can say 2 pi times the frequency is 8.2 over a second, which means that the frequency is 8.2 divided by 2 pi times a second. So 8.2, and again, if you're doing this in your calculator, don't just say divided by 2 pi. What that'll do is divide by 2 and then multiply by pi. So I'm going to divide by 2 and hit enter, and then I'm going to divide by pi. So I'm getting about 1.3 per second, or 1.3 hertz. So yeah, you should be able to do this kind of both ways. If you're given the information about the wave, like its frequency and wavelength, you should be able to write down the description of the wave. And if you are given this mathematical description, you should be able to get out of it the frequency and the wavelength. Okay, so are there any questions on anything? Okay, so that'll be it for today. And again, I really hope this recording works, so I can just post it on YouTube, and then I'll attach a link. I'll figure out where to put it, but if there's no questions, that'll be it for today then.